This is your next notes video on classifying and measuring stars. We do this with something called an HR or Hertzsprung-Russell diagram. You don't need to know who it's named after, just that this is a diagram that we use to measure different properties of stars. So we know that all stars can have different temperatures, luminosities, sizes, masses, different distances. So we use this sort of diagram to help us classify them. And this is specifically looking at measuring luminosity versus the temperature. And remember that temperature and spectral type or color go hand in hand. So we could think about an HR diagram measuring characteristics of stars just like we could plot someone's height versus weight. And if we were to look at the majority of all humans, their height and weight would correlate. So we could see with an increase in height, we would generally have an increase in weight and vice versa. But there can be anomalies to that. We can have exceptions. We could have, supermodels that could have a very low weight and be over here. We could have very short, very obese people, which could be over here. So there can definitely be some exceptions, just as there are to stars. So we could think about this area in the middle, which we're going to call the main sequence, as being the average, where most people are going to follow that linear relationship. So also do stars. So we could see that stars are going to increase in luminosity with an increase in temperature. That's generally the relationship. So here we can see what the plot of stars would look like. And here is what we call the main sequence. We can see that we have lower temperature on the right, higher temperature on the left. And we can see our temperature, luminosity, we can see our spectral classification, and then we can see the areas of anomalies where we have our supergiants, our red giants, and our white dwarfs. We're going to talk more about stellar evolution next week, but right now, we're just going to look at the types of stars, how we classify them. We're not necessarily going to be looking at the differences or their life cycles or the things that differentiate them. We're just looking at how to measure them. So along that main sequence, even though that is an area that can be thought of as an average, and that's an area where most all stars fall, we can still break up that main sequence into dwarf stars, mid-mass stars, and high-mass stars. So all stars on the main sequence have in common is that they are all in about the middle stage of their life. They're all stable. So we find 90% of stars there because stars spend 90% of their life there. There, they're actively fusing hydrogen to make helium. For higher mass stars, they would eventually fuse heavier and heavier elements. So they're just going through the process of fusion to create heavier elements from lighter elements until they run out of hydrogen. So along the main sequence, they're all characterized by hydrogen fusion, and they're all stable. So then off of the main sequence, we would have stars that have evolved where they no longer have hydrogen in their cores. So we would have our giant stars, our supergiants, and then for sun-like stars, we would have our white dwarfs. Black dwarfs are a hypothetical object. We know that they can exist. We just don't have a universe that is old enough to produce them yet. So white dwarfs that are in the bottom left-hand corner of the HR diagram, white dwarfs are just a star like our sun that is eventually run out of fuel, and it is just a glowing hot core. When that core suddenly doesn't have any luminosity left, it eventually just cools off. It becomes a black dwarf. But that would take about 30 billion years to produce, and our universe just isn't as old as that. We've only had sun-like stars for about the last 8 billion years. Our sun is about 5 billion years old, so it's going to be a white dwarf in another 5 billion years, and a black dwarf probably 5 to 10 billion years after that. So our universe just isn't old enough to produce them, and even if there was, we would have no way of detecting them. They'd be very small, they'd have very low mass, very low gravity, and they wouldn't produce any of their own light. So one of the cool things about the HR diagram is it's not generally used just to plot an individual star, but to plot clusters, because when we look at clusters of stars, we notice that they all have very similar compositions, very similar characteristics. So in terms of their distance, their radius, their mass, their luminosity class, and we can also then plot their age. And that's a really important function of using the HR diagram to look at clusters, is knowing where in the life cycle not just the individual stars are, but the cluster as a whole. So here is a fully developed HR diagram. We can see that as we move from the bottom right to the upper left, our size is going to increase. We can see that we have giants over here. If you notice these arrows, notice they only extend from the upper portion of the HR diagram. And that's because our very smaller stars, they they evolve to red giants, but they never become supergiants. So the evolution is much different for stars in this portion of the diagram than it is for stars in this portion of the diagram. We can see our white dwarf stars over here, very small radius, very hot, so very luminous. Here we have a much larger radius. These are very luminous because of their size, but we can see that they're not very hot. These are also very cool. So we can see this change throughout the main sequence. And remember, we've got our lower range, or our dwarf stars, our mid-range, which is what our sun is. Our sun's right about there. And then our high-mass main sequence stars. And for our purposes, for stars, we're going to call massive and giant two separate things. So massive stars would be located up here, and that is a type of star, whereas giants located here is a phase, so two different things. So here we can see some common stars and how their radii compare. We can see that we have these dashed lines of radius that separate out the HR diagram. So here we could see anything along that line is about the same radius as the sun, increasing as we move up the diagram. We can see Polaris, Rigel, and Betelgeuse, which make up the foot and the shoulder of Orion. And we can also see that we have increasing mass. And what correlates directly with mass is life cycle. So the lower mass the star, the longer it lives. We can see that stars of 0.1 solar mass can live up to 3 trillion years. Remember, our universe is only 15 billion years old. So our sun, right about the middle, is can have lived about 10 billion years. And as we move up the diagram, we get stars that are only living to be a few million years old, as low as under 10 million years old. So higher mass stars have much shorter lifetimes because they are burning their fuel at a significantly higher rate. So even though these have less, they burn it slower. So the consequence of that is that we have a universe that is full of cool red stars that are not very old. So we can see, again, look in here, that for stars around the mass of our sun, we can see how long that they can live and what their corresponding spectral type would be. And then as we increase in solar mass, that lifetime gets significantly smaller. So these stars that don't live very long don't populate the universe. These cooler ones do. So if we were to look and extend out from the Earth about 62 parsecs out, we could see what our immediate solar neighborhood would be. And you looked at a lot of these stars in the classification activity in class. So these are the stars that are very close to the sun, which would all have pretty similar characteristics to the sun, born of the same condensing nebula in the same region of the Milky Way. And if you take a look and really kind of stare at this graph, this is a three-dimensional representation of the HR diagram. We could see that down here would be our bottom left, over here would be our bottom right, there's our main sequence, here's our supergiant region. And if we were to populate that with stars in our immediate solar neighborhood, we can see that we have predominantly red dwarf stars. We have some white dwarf stars because our cluster is mid-range to older, and we have very few stars that are bigger. You can see we have no supergiants and no giants left. We have all from the middle of the main sequence down, but the presence of white dwarfs tells us about the age. That tells us that there are stars that are older. But these fainter stars are significantly harder to observe, as we saw that some of these can only be observed in the infrared. So looking at star clusters in the HR can tell us about their age. And when we look right here at this point, we call this the turn-off point. This is the point at which stars begin to turn off. And we can see that for very young clusters, that turn-off point is going to be up here. So initially you'll have a full main sequence of any given cluster. You'll have a good spread of stars, because remember, that's the average. But the older stars that live shorter lives are going to turn off first. So as the cluster increases in age, this turn-off point gets lower and lower and lower. But we can see that with really young clusters, you can have stars over here that haven't even reached main sequence yet, that would only be visible in the infrared, that are not hot enough to complete fusion. So we can see that we've got a pretty full developed giant branch, and we have a few white dwarf stars in this region down here. So this tells us that this cluster is about mid-age. So one of the things I would expect you to know would be to tell me which of these clusters is the oldest and the youngest. And remember, we want to take a look at that turn-off point. And our other indication, if there is no turn-off point, is looking at how many stars have actually reached main sequence, because the younger, hotter stars are going to reach main sequence first before the older, cooler, dimmer stars. And that is where we are going to end for today. We will pick up with binary stars next time. Have a great day.